Well, good day, pre-calcers. I hope you guys are doing well today. We are getting ready to start another lesson. This one is really an extension of what we did yesterday. We are going to focus on solving inequalities. All right, solving inequalities. And the types of inequalities we're going to solve are going to be quadratic, rational, and radical inequalities. So all the techniques that you re-practiced yesterday on solving those types of equations will be used today when you solve inequalities. Our objectives for today is you will solve inequalities using algebra so that you can understand how to apply inequality thinking to other math problem situations. And all those will occur in the future. And you know that you will understand it if you can self-check and self-correct your work and errors. So there you go. That's our goal for today. So let's jump right in and start talking about inequalities. So the first thing that I want to remind you about inequalities is there are several ways that we can write our answers. All right? If you remember in Algebra 1, we often like to graph our answer to an inequality. So if you had like x is greater than 1, you would make a number line and then you would draw greater than 1 using an open circle to represent it was not equal to 1. Or you might have x is less than or equal to -2, and you put -2, and you would use a closed circle to represent that it could equal it. So that would be a graph. The other way we could write our answers is we could write them as an inequality. So we'd actually write the inequality. We'd solve a simple linear inequality, and we get x is greater than 1 or x is less than or equal to 2. So finally, the last way to write answers is what is called interval notation. And despite what you think or may have thought in the past, interval notation is the standard. It's the way most mathematicians talk and write about intervals on a number line. And so we need to review what our answers are going to look like in interval notation. Now, just so you remember, let's do something like this. X greater than A, X less than A. Then X greater than or equal to A, X less than or equal to A. And then we might have something like A is less than X is less than B. A is less than or equal to X is less than or equal to B. And then we could have what we call half open. A is less than X, less than or equal to B, or A is less than or equal to X is less than B. So there are essentially 8 situations here in terms of interval notation. Now, fortunately, we have a quick example up here that we would like to look at. We have x is greater than 1, and we see its graph right here, x is greater than 1. So what happens essentially in interval notation is when we look at the number line, we not only label the 1, but we also label the endpoints of the number line. Where does it go? Well, it goes to negative infinity on the left and positive infinity on the right. So, and then instead of an open circle, we use a parenthesis. And so this would also be a correct graph. But this also shows us how to do the interval notation. We would say 1, which is the leftmost spot in the interval, it is not equal to that, so we use a parenthesis. And then it goes to positive infinity, and it can never equal that because it goes forever, so you also use that. And so this would be the open interval from 1 to infinity, and that would represent x is greater than 1. Okay? And we use parentheses instead of open circles. All right? And once you've kind of got that pattern, that'll help you to do the rest of these. So x is greater than a always looks like a to infinity. X is less than a looks like negative infinity to a. X greater than or equal to a, that's a closed interval because it's greater than or equal. So that would look like a to infinity. Now notice the infinity, we're still not equal to that, so it's open. But the a, we are equal to the a, so we used a closed bracket instead of a parenthesis. X less than or equal to a is negative infinity to a. And then we can do the finite intervals between two finite numbers. So you get from a to b, but not including a or b. From a to b, but we include both a and b. And then on the last two, we go from a to b, but we include b, but we don't include a. These are called half open intervals. But all parentheses, this one, this one, this one, those are all called open intervals. All right. And then the ones where you have both brackets are equal, those are called closed intervals. Okay? So half open, open, closed intervals. And then finally the last one, a is less than or equal to x is less than b, also half open, but we're equal to a, but we're not equal to b. And so this is interval notation. You always want to write the inequality, the number line, and the appropriate interval. Okay? And that's a reminder of something we did in Algebra 2, but maybe we didn't use it all the time. But we in pre-calculus will use it all the time. And so we are to part 1, solving quadratic inequalities. So let's grab a quick example. Let's try this one here. Yeah, let's go with 6x squared minus 5x equals 6. Okay, so we are set to, let's make it less than or equal. So now it's an inequality. We're going to solve a quadratic inequality. Now, when we solve quadratic equations, we had to set them equal to 0. So the same exact thing applies to a quadratic inequality, except it needs to be less than or greater than 0. So go ahead and take your equation and get it to 0. So we're going to subtract 6 from both sides. And we get 6x squared minus 5x minus 6 is less than or equal to 0. All right. And then we proceed and we're going to factor or use the quadratic formula. All right. And so to do that, In this case, I believe we can factor. And so we're going to do 3x and 2x. And so let's do minus 3 and plus 2. So this will be 2 times negative 3 is negative 6. 3x times 2x is 6x squared. And then I get plus 4x minus 9x, which gives me a negative 5x. So that is a correct factoring. Now, it's at this point that the problem begins to deviate. And we need to then gain a geometric understanding of what is solving an inequality really doing. So, before we finish this problem, let's go back to the original problem. So what you're saying is 6x squared minus 5x is less than or equal to 6. So what does that really mean? So let's scoot up here and let's do a little Desmos moment, all right? Go to the browser. Let me shrink it down a little so we have some room to finish solving. All right, and what we're going to do is we're going to take the 6x squared minus 5x. So 6x squared minus 5x. That is the left side. The right side was 6. So we're going to put y equals 6. Okay? Now, as you can see, this gives us two graphs. This gives us the parabola for the 6x squared minus 5x, and it gives us y equals 6. Now, what we're saying is, we're saying that the graph of 6x squared minus 5x is less than or equal to 6. That's our original inequality. So what are we trying to do? Well, we ask ourselves, where is the graph less than or equal to 6? Okay? Where's the graph less than or equal to 6? Well, what we notice is that these two graphs intersect at these points. And if you'll notice, the parabola is above here. It's below the line in between those 2 points, and then it's above to the right of the other point. And so, without knowing what those points are, in fact, I don't even need to know what those points are. I have an understanding of what this inequality means. It means the graph of 6x squared minus 5x, where is it going to be below the graph of 6? Because less than or equal means below, greater than means above, right? So we want to know where the y values for this are smaller than the y values equal to 6. And we can see on the graph that this part of the graph right here is where those y values are below y equals 6. Okay? So that's a beautiful thing. This tells us geometrically what we're going to do algebraically. Now, when we transform this equation by subtracting 6 from both sides and getting it equal to 0, what does that do? Well, what that does, and I'm gonna, a little erasing here. Where's the eraser? Ah, there it is. So let me do a little erasing on this graph. So when I subtract 6 from both sides, it's like I'm subtracting 6 from each of these graphs. So what does that end up doing when I subtract 6? Well, it lowers all these points by 6. So the horizontal line now becomes the x-axis. And this graph up here gets moved down 6 units. So what are we saying here? We're asking the question, where is the graph of this quadratic less than or equal to 0 or below the x-axis? So we have now interpreted this inequality as meaning below the x-axis. That means where these points intersect, right there and right there, those points are now x-intercepts. And so when we think about solving this problem, what we want to do at this point is really find the x-intercepts. So we take 3x plus 2 equals 0 and 2x minus 3 equals 0. And that gives us 3x equals negative 2, x equals negative 2/3, and 2x equals 3, x equals 3/2. And so these are the x-intercepts. Oftentimes we'll call them critical points. And these critical points are critical because somewhere around those points, the graph will either be above or below or above. All right? And so the x-intercepts, the 0 is the dividing line between switching whether a graph is below the x-axis or above the x-axis, because 0 separates positive numbers from negative numbers. So in solving this quadratic inequality, we have to find these x-intercepts, okay? Now, once we have the x-intercepts, we can then make a number line. And on this number line, I have 3/2 and negative 2/3. So here's 0. So 3/2 is over here, and negative 2/3 is here. Sort of looks like this graph right here, right? I got 2 points. And what I know is, since this is a 6x squared, a positive ax squared, I know that this is really some kind of parabola that goes through this number line in this manner. And so what I need to do is just check values to see if I get above, which means positive values, or I get a below, which means I'm getting a negative value, okay? And since the negative 2/3 and the 3/2 divide up the number line, we pick what we call them test values, okay? So I just need a number less than negative 2/3. So negative 2 is a test value. I need a number between negative 2/3 and 3/2. Let's pick 0. That's a test value. And then let's pick 2 as a value bigger than 3/2. So then what you have to do is you have to check if inequality is true or false. If it's true, that's an answer to your question. If it's false, that's not an answer to your question. So all I do is I take the -2 and I plug it into the factored form of our inequality. So we had 3x plus 2 times 2x minus 3 is less than or equal to 0. So these are my x values, -2, 0, 2. All right? So I take -2 and I plug it in. 3 times -2 plus 2. 2 times -2 minus 3. And so I want to check that. That's a -6 plus 2, which is -4. That's a -4 minus 3, which is -7. -4 times -7 is positive 28, which is not less than or equal to 0. So it's not a solution. So we have x, and then we have a conclusion, not less than or equal to 0. Okay? It's 28, it's not less than or equal to 0. So every value in this interval is not a solution. Okay? So now we check 0. So 3 times 0 plus 2 times 2 times 0 minus 3. That is 2 times -3, which is equal to -6, which is less than or equal to 0. So it matches our inequality. Therefore, 0, our conclusion is it is a solution. All right. And the answer is the interval from -2/3 to 3/2. Okay. Now, since it's less than or equal, we would put brackets instead of parentheses. Okay. Now, we still have to check this 2 over here to see if it works. All right. And so 3 times 2 plus 2. 2 times 2 plus minus 3. And that is 8 times 1, which is 8, which is not less than or equal to 0. It's close, but it's not equal to that. So our conclusion here is it's not less than or equal to 0. Now, you have just watched the whole process. I've gone through the theory, why it works, and we're going to do another problem here a little faster, and I'll show you how I do it. And I've sort of simulated a little table here about where you can put your test values and conclusions, and I'll make that a little neater in the next problem we do. So we're going to do another problem now. All right? Okay, let's do another quadratic inequality, just so you can see the whole process and how I might do it all the way through. Okay? Let's try this one. Suppose I have 2x times x plus 2 is greater than 3. Okay? So I'm going to just proceed and you can kind of watch. So the first thing you can see is I have now set it to greater than 0. Now I'm going to proceed. I don't think this one factors, so in this case I have to use the quadratic formula. But again, since I'm checking for equal to 0, I'm really finding the x-intercepts where the graph crosses the x-axis right here. Okay, so now I've used the quadratic formula to help solve for when this quadratic is equal to 0. In other words, I'm finding the x-intercepts. I'm looking to see where this quadratic equation intersects the x-axis. And since it's a 2x squared, I know it'll look like this rather than like this. And I'm looking for the part then that will be above the x-axis, okay? So in this case, I'll probably be looking for those two tails. But in order to do that, I need these intercepts. Now, very often when your intercepts are like this, you might want to convert those into a decimal just so you can visualize it a little bit better. So let's do that. So in order to do that, I'm going to use my scientific calculator, Desmo scientific calculator, right here. Okay. Let me move this over just a little more, just so it doesn't hide the work. Okay, now I'm going to use the scientific calculator. So I'll do -2 plus the square root of 10. All right. Now, the trick here is when I hit divide, notice how it's only dividing the square root of 10. So that's not correct. So I got to undo this a little bit and ask myself, what's the problem here? There. So I hit the back button. What's the issue? Well, the issue is, since that's a numerator, I have to put everything in the numerator and I'm dividing the whole thing by 2. So this is something very important you need to do on your calculator as you check it. Now, we can see that 0.581 is fairly close to what we want there. And then let's do the next one. All right. So we'll do the parentheses right off the bat. -2 minus the square root of 10. Divided by 2. Whoops. Is equal to -2.58. Okay? And so now that we have those, 0.581 and -2.581, we can now set up our number line. Okay? And so here's our number line. And I know that I have a -2.581 and I have a 0.581. And I need a test value in each interval. So -3, 0, and 1. So these are test values. Okay? All right? And then I need a conclusion in each case. A conclusion. Is it above or below the axis? All right? So I take the -3 and I now need to plug it in to this form of the equation to see. So I'm going to take 2. Now if it's factored, I usually like to do that. It's often easier, but I can do it even when it doesn't factor. And we're trying to see if this is bigger than 0. So -3 squared is 9, so this will be 18 minus 12 minus 3 equals 3, which is greater than 0. Okay? So our conclusion is that we are above the x-axis here, which means we are greater than 0. So this is an interval I want to include in my answer. Okay? Now we do the next check. 2 times 0 squared plus 4 times 0 minus 3. And that'll give us -3, which is less than 0. So what's our conclusion there? Below the x-axis. Not greater than 0. Okay? Because it's actually less than 0. All right? And then we check our final value of 1. 2 times 1 squared plus 4 times 1 minus 3 is equal to 2 plus 4 is 6, is equal to 3, which is bigger than 0. So that's a true inequality. And so our conclusion is we are above the x-axis. We are actually greater than 0 there. So this is an answer to the inequality. So now, given all that work, I need to write my answer. My answer will be 2 intervals. So I'm going to do both intervals together. So I use union. It's this one and it's this one. And so since we're on a number line, this is -infinity. So we go from -infinity up to -2.58. But we don't include that. All right. And if you wish, you could actually write -2 minus square root of 10 over 2 in place of the decimal. All right? And then you go over to the next one, and it's 0.581 up to positive infinity. And so this would be the solution, which is, where is 2x times x plus 2 greater than 3? Well, since it's a quadratic inequality, I have now shown and concluded that it's here. Now, one more thing. Remember, I said you need to be able to self-check yourself. So now we're going to do a quick self-check, okay? Remember, pre-calculus is primarily an applied algebra course. We must understand all the algebra, okay? So you need to know how to do this. And the only way you're going to know how to do what I've just done is to practice, okay? The next thing that I want to say is that once you do the algebra and you interpret what it means, which is what we've done here and here, okay, then you can often check it graphically, okay? Now, I'm pretty comfortable that I've done this right, but I would like to make sure. So once again, let's go grab Desmos or a graphing calculator, and we're just going to graph this. And we're going to do the original, okay? The original problem was 2x times x plus 2 is greater than 3. So we'll try that. 2x times x plus 2. Okay. And then we want to put y equals 3, because you can't just put a number there. You have to make it y equals 3. And so we want to know where the red graph is above the blue graph. Well, where does that occur? If you click on this point, it occurs from x equals -2.581. Hey, that's the number we got. So from negative infinity to -2.581, the red graph is above the blue graph. It's greater than 3. And for 0.581 to positive infinity, the red graph is above the blue graph. Okay? So I now know that I have done that problem completely correctly. All right? Boom. Nice. Do you like it? That's how you guys can do algebra and then know that you're doing the algebra correct. We're not about getting just answers anymore. We're about understanding whether we know how to do things. Okay? And that is very important. The more you understand, the better you get at mathematics. All right, let's move on to our other equations. We can check them in exactly the same way graphically, but they solve a little bit differently. So now we're going to solve rational inequalities. So it turns out when you solve a rational inequality that it's slightly different from the other inequalities, okay? And the quadratic inequality or solving a rational equation, because in this case you want to keep the denominators. You never want to clear denominators, and I'll show you why in just a moment. Okay, so I'm just trying to snag an example here, which disappeared from my view. And I've got it right here if I can find it. All right. So let's go ahead and solve. So let's pick an equation. Suppose I have 2 over x plus 1 is greater than 4. And let's make it greater than or equal to 4. So I want to be able to solve that rational inequality. Now, normally, if it was an equation, we would multiply both sides by x plus 1. But let me ask you a question. Is x plus 1 a positive, or is it a negative number, or could it possibly be either one? So think about that for a second. And the answer is it could be either. It depends on the value of x, but x plus 1 as an expression could represent any value, positive or negative. So, and if it happened to be negative, then we have to change the direction of the inequality. Remember, if you multiply both sides by a negative, you have to flip the inequality. So, since that's the case, we have to keep the common denominator. We can't get rid of it. And so the best way to do this problem is first get it greater than or less than 0. So you get 2 over x plus 1 minus 4 is greater than or equal to 0. So again, we're going to be comparing with 0, so we want to find the x-intercepts of this thing right here. So what do I do in this case? Well, my common denominator is x plus 1. So what I want to do is I want to multiply the 4 times x plus 1 over x plus 1. So I end up with the common denominator. And so that leaves me 2 over x plus 1 minus, so this is a negative 4 times x plus 1. So it's minus, okay, this is a little tricky. I would leave it like this right now, okay? Over x plus 1. I'll tell you what to do in a minute. What happens when you multiply it. So that's where we're at in this case. Okay, we now have a common denominator. When our denominator is common, we can add the numerators, add or subtract them. So the numerator is 2 minus 4 times x plus 1 over x plus 1. Now, being very specific, not doing anything with this negative sign until I get everything all together in one fraction. So I get 2 minus 4x minus 4 over x plus 1, which is negative 4x minus 2 over x plus 1 is greater than or equal to 0. So what we have done is we have combined everything into one fraction. So this is your goal. Combine all non-zero terms into one fraction. Okay? Once you are there, then you can do the number line game. You can find the x-intercepts. And so with rational functions, you take the numerator and the denominator and you set them equal to 0. Because it can't be undefined either. And so I now have my zeros. So then I can make a number line. Okay. That number line, -1 and -1/2. So -1 and -1/2. There, I've split my number line up. I can choose test values. So let's pick -2, -0.75, which is between those two, and 0. Okay? And then we are going to want to write a conclusion, okay, when we're done. So at this point, we need to take our test value and plug it into our simplified equation. Since we could simplify it, we can plug in the test values there. So we're going to have -4 times -2 minus 2 over -2 plus 1, which is equal to 8 minus 2, or 6, over -1, which is -6, which is that greater than or equal to 0? And the answer is no, it's not. So right here on this graph, it is not above the x-axis. All right. And so then you do your next test value. So -4 times -0.75 minus 2 over -0.75 plus 1. So this is 0.25. And the numerator is 3 minus 2, 1. So that's equal to 4, which is greater than or equal to 0. Okay, so our conclusion here is it is above the x-axis. Okay, so this is an answer. That area, not the 0.75, but that region on the number line. And then our last test value is 0. So -4 times 0 minus 2 over 0 plus 1 is -2 over 1, which is not greater than 0. So this means not above x-axis. So our only solution is that interval there, which goes from -1 to -1/2. Now, it's greater than. And notice, which number does -1 make the denominator 0? It does. So we cannot include it. Okay? Even though it's greater than or equal. So you must check that. Okay? So you have to note that it's undefined at x equals -1. Okay? And this would be our solution. So once again, let's check it on a Desmos graph. Okay? All right, and let me shrink it just a little. And so our original problem was 2 divided by x plus 1. Okay, and then we had y equals 4. Okay, and we want the part of the graph which is greater than 4. So the 0 we're looking for is this one. All right. Notice how that is -0.5. Okay. And the graph here, if you look, it's above -0.5. But for how far? Now, there's another thing they don't show on this graph, but if you remember, there's a vertical asymptote here, x equals -1, and I just drew that in there. That was the other 0. And you'll notice that from that green line up to this point right here, the -1 to -1/2, that is the only place that the graph is above the x-axis or above the original line. When you solve it and move it down to the x-axis, all the stuff just gets moved to the x-axis and you can see it. But, so graphically, I have now confirmed I did it correct. So I'm completely comfortable with that problem. Okay? That's a very typical rational inequality. And so we are now ready for part 3, radical inequalities. So a good example would be like the square root of 3x minus 5 is less than 2. Okay? And so, since it's a radical, we're going to proceed like normal, and we're going to square both sides. So we get 3x minus 5 is less than 4. So 3x is less, since it's linear now, we solve like a linear, which means isolate the x. So add 5, 3x is less than 9. Divide by 3 and get x is less than 3. All right, which in interval notation is -infinity to 3. All right, or less than 3, sorry. Not a bracket, parenthesis there. I apologize. Okay, so now that we have solved that radical inequality, pretty much like solving a radical equation, we can check it geometrically. So let's do our check. All right. And 3x minus 5 is less than 2. So square root of 3x minus 5 y equals 2. All right. And now you can see we're asking where is the graph, the red graph, smaller than the blue graph. And if we look at this, we can see that the red graph, here's where they intersect at x equals 3, and the red graph is smaller than the blue graph in this range at x is less than 3. All right. Now, there's one other issue, and oh, I messed this one up. I clicked on it and blew it out. But the main thing is at this point is the 3x minus 5, we need to remember the domain of that particular equation. And so the 3x minus 5 always has to be greater than or equal to 0. And so you can see right here, 5/3 is 1 2/3, that this red graph only appears to be the only part of the graph on the square root. And so even though we said the solution is x is less than 3, we could have said it also has to be bigger than 5/3. All right. Although they weren't asking us a domain question there, and this is good enough, but it might have wanted this solution. And I don't think I've encountered it in your lessons yet before, but there may be a radical equation where something like this happens, where you have to check the domain as well, because the graph doesn't go on forever completely less than 3. It just stops at 5/3. So it's really 5/3 less than x is less than 3 in this particular case. All right, let's do another one and then I'll let you go. So another radical equation. Let's go with x is greater than or equal to 2 times square root of x minus 1. So we're going to go ahead and square both sides. So we get x squared is greater than or equal to 4 times x minus 1. And this gives x squared is greater than or equal to 4x minus 4, which is now a quadratic inequality. So sometimes a radical will turn into a quadratic. Since it's a quadratic, now you have to solve it according to those methods. Okay? Which is, you could use factoring here. And so the critical point is only 2. And then you would pick test values. And then check them into you would check these values and then write a conclusion. So my test value is 0. So 0 minus 2 times 0 minus 2 is a positive 4, which is bigger than 0. And 3 minus 2, and 3 minus 2 is 1 times 1 is 1, which is also bigger than 0. So both of these intervals work. All right? And so one of these graphs is always above the other graph. Again, we can confirm that with Desmos. All right? So let's do that. So we're going to take x. And then the other one is 2 times square root of x minus 1. And as you can see, wherever the red graph is, it's always above the blue graph. And that's a nice thing. Okay? The red graph is always above the blue graph. And that's actually what we could see by the picture and the problem. Okay? So radicals. So sometimes they end up being linear. Sometimes they end up being quadratic. So you got to kind of pay attention to that as well.